So earlier in Unit 10, we talked about how to solve quadratics by either factoring, by using the square root, or even by a graph or a table. What we're going to do today is take a look at how to solve quadratics using the quadratic formula. Now, the quadratic formula is going to be able to be used at any moment in time to solve quadratics. So you don't necessarily have to use those other methods we talked about, although those might be quicker to do. But in particular, the quadratic formula is going to be great when we know that we might have solutions that are those imaginary solutions, right? So they're not those real solutions we were kind of seeing when we were originally solving these. So let's go ahead and quickly kind of put what our quadratic formula is and how we can use it and all of that, okay? So here what we're going to do is using quadratic formula to solve um, for the solutions of quadratic equations, okay? It's kind of a long one, but just kind of emphasizing what we're doing, right? So we're going to be using the quadratic formula to essentially solve the solutions of our quadratic equation. So we'll start off with our formula, and our formula, right, our quadratic equation formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, now here, of course, we're using the form we talked about previously, which is our function y equals ax squared plus bx plus c. Okay, so you're pulling the a, b, and c values from our equation, and you're just going to pop them into this, this formula and solve for the x values that would solve the quadratic. Okay, that would be solutions. With this, notice a couple things. So with this, we see this kind of plus or minus right here. This means that we have the potential to have two solutions, right? So let's spell solutions right here, right? Solutions. um, because the plus or minus, right? So you could have, let's say, a positive 4 and a negative 4, right? The plus or minus will produce those two options for us. We also should kind of notice that this part right here under the square root, this b squared minus 4ac, this is known as the discriminant. Okay, so this is known as the discriminant. I'm going to call this abbreviated just D. Okay, so when I use this in the future, I'm just going to use D to abbreviate it so I don't have to write the discriminant over and over and over again. But this part under the square root right here, b squared minus 4ac, that is known as the discriminant. Now, the discriminant is going to be useful because if that value of D is greater than 0, so think about you get a positive number under here. We talked about you can take the square root of a positive number, and if you do, then you would have plus or minus that thing. This would tell us then that we would have two real solutions, right? So our quadratic is going to have two real solutions if this number, this discriminant under the square root, is a positive number, okay? Now, if that value is 0, right? If our discriminant is 0, well, imagine if this is 0, then you're adding or subtracting 0, which wouldn't change anything, right? Plus or minus, that thing wouldn't matter because it's just 0. You would have one solution, which would be negative b over 2a, right? Because this would all go to 0. So there you would have only one solution. And so we label this here, we'd have one real solution. And you can then maybe imagine that if d is less than 0, so your discriminant is a negative number, what is that going to mean? Well, this is going to mean that we have 0 real solutions. This is because, remember, we talked about you cannot take the square root of a negative number, right? This is an even root here. This is the square root. So you cannot do that of a negative number. However, we're going to have, we don't have two, no real, we have no real, but we have two, what I'm going to call complex or imaginary solutions. Okay, so we have no real, but we have two complex solutions. Okay, so let's kind of do some problems where I just try and use the quadratic formula. Note again, we could do these other techniques, right? We could factor. If it's set up to do so, we could potentially use like the square root or something, but I just want to get us comfortable plugging into this formula. This will be a formula that we have to memorize, okay? So you do need to memorize this quadratic formula here. And it would be obviously very good to know what it means when each value, or what the discriminant is versus what the solutions come out to be, right? So if I have positive, 0, or negative discriminant, what that means for the number of solutions. Okay, so let's try an example, and I'll see if I can leave our formula in as long as I can. Let's say I'm given negative 20x squared minus 2x plus 6 equals 0. Okay, so the fact that this is equal to 0 means that I'm going to solve these just like I would normally do, right? I'm trying to find essentially this, which is the y value being equal to 0. Those are going to be the x-intercepts, which is what this formula solves for, right? We're getting solutions, x-intercepts, blah, 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 right? They could also just give me y equals this and ask me to find the solutions or x-intercepts, right? That's equivalent to saying what we see here, okay? So if you give this equation, then you ask for x-intercepts or solutions, that's the same thing as just giving this, okay? I don't have to use words now because this being equal to 0 satisfies that, right? Being an x-intercept, essentially. So let's say I wanted to solve this. Obviously, there might be some factoring I could do here. I don't know. This kind of looks like a complicated one. I might be sitting here for a while to factor this, and it might not even factor into nice integers, right? So I have no idea. So what I'm gonna do is I'm just gonna go straight away and try the quadratic, right? Let's try the quadratic formula, see what we get. So the x values that would satisfy this would be negative b, so negative 2, plus or minus the square root of b squared, negative 2 squared, minus 4a, 20, negative 20, sorry, and c, which is 6, all over 2a, 2 times negative 20. Okay, so literally just taking our a, b, and c values, plugging them directly in here, and getting the output, right? So again, let me label this. A is negative 20, b is negative 2, and c is 6, okay? Just the coefficients, right? You do not include the x's at all here, right? A is the number in front, b is the number in front, right? You're not taking the x's. From here, we simplify a bit. Negative 2, positive 2, plus or minus 4 plus 80 times 6, which would be 480 over negative 40. From here, that's 2 plus or minus root 484 over negative 40. 484, we're going to have to simplify this. That actually does become a perfect square. It is this square root of 44 is 22. Again, you might want to maybe do a factor tree or something like that to break that apart. But either way, we should come out to this. You can even maybe just plug in your calculator to see that. But if you're doing it by hand, of course, you might want to do a factor tree. And then this ends up being what? Well, either 2 plus 22, so 24 over negative 40, or it becomes 2 minus 22 over negative 40, right? So the plus or minus is going to give me two solutions here. I'm either going to get 24 over negative 40, or I'm going to get negative 20 over negative 40. And so I'll just put that here, negative 20. So this is negative 3/5, right, on this one, or this is going to be a half, right? So this could be this or this. And so therefore x could be negative 3/5 and 1/2, right? These are the solutions. These are the intercepts, okay? Note how if we look back to our discriminant, right? So we look here, we got a positive number, right? Positive 484. That meant that we were going to get two real solutions. And we found two real solutions, right? So this is kind of one of the nice things about the quadratic formula, right? One of the interesting properties that is actually going to be very useful for us is that without even solving the actual solutions, right, getting the final values, we can check to see if there is 2, 1, or 0 real. And then with that, obviously, if there's 2 complex, right? So we can just literally calculate b squared minus 4ac, see what you get, and then that will be kind of a determining factor if you should continue to follow the steps, right? Because if you know this is obviously a negative number and you're looking for real solutions, you might just stop, right? Okay. Hopefully this is making some sense. We're going to do another one. Again, all we're going to be doing is kind of plug in directly into our quadratic formula. So let's say we're given negative 12x squared equals 11x plus 2. And not that far off from what we know, right? Obviously, we want to move everything to one side, right? We're always trying to solve our thing equal to 0. Okay, this is the pattern. Always, always, always move the terms over, try and solve it equal to 0. So this becomes, if I move it all to the right, which seems pretty beneficial to me because I already have 2 terms on the right, I send this guy over, 12x squared plus 11x plus 2, that's all going to equal 0. Okay, now I go ahead and use the quadratic formula. So I get negative b, negative 11, plus or minus square root of b squared minus 4ac all over 2a, right? Again, we should know what a, b, and c are just from looking at this after we've done a couple of these. So we get negative 11 plus or minus 11 squared, 121, 4 times 12, we can get 48 times 2 would be 96, all over 2 and 12, which is 24. Keep simplifying, negative 11 plus or minus 121 minus 96 is 25. Therefore, negative 11 plus or minus 5 over 24. What does that tell us? Well, this tells us that I either get negative 11 minus 5, which would be negative 16 over 24, or I get negative 11 plus 5, which would be negative 6 over 24. And we can go ahead and simplify those. That's negative 2/3, and then this one is negative 1/4. So our solutions, right, our x values would be negative 2/3 and negative 1/4. Okay, same thought process as last time, right? We look at the discriminant. We saw it was positive 25. That immediately told us that we would have our 2 real solutions, and we did have 2 real solutions, right? So d greater than 0, therefore 2 real. Great. Okay. Now, obviously, I'm solving all these out. There might be a question where they just ask you how many solutions there are. They don't ask you what the solutions are. They just want to know how many. So you don't have to plug into the full thing, of course, right? So you don't have to do all of the quadratic formula. You literally would just have to check the b squared minus 4ac. Okay. So if we're only asking for the types of solutions, not the actual values, just do this, right? Just solve the discriminant. We find that to be 25. That will immediately tell us greater than 0. Therefore, 2 real solutions. You're done and done, right? If that was the question. Okay, cool. Not too bad. Let's go ahead and look at another one. One more for using our quadratic formula. Let's say I'm left with x squared minus 3x plus 3/2 equal to 0. Note how here, the only difference in what we've had previously was that we now have a fraction for one of our coefficients, right? Our c value. Doesn't matter, right? Does not matter. It's still a number. We can still plug into the formula. Doesn't matter. So here we go and say, okay, let's try the quadratic formula. Negative b, negative negative 3, plus or minus square root of b squared minus 4ac all over 2 times a. Remember, a here is 1, right? The coefficient in front of x squared is 1x squared. So that's our a. We go ahead and simplify this. 3 plus or minus negative 3 squared is 9. 4 times 3 is 12. 12 over 2 is 6. So minus 6 all over 2. This is root 3. This would be a sufficient answer, right? Obviously, if our system requires us to plug in, you might put 3 minus root 3 over 2, and then you might put 3 plus root 3 over 2, right? If we can't use our plus or minus, but these are equivalent, okay? So this and this are great. And again, as we expected, this was equal to positive 3, which meant we would have 2 real solutions, and we do, right? These are 2 real solutions. So, okay, perfect. This is using the quadratic formula, right? If we ever want to determine what and how many of our solutions, real or complex, that we have, we would probably use the discriminant. And then if we want to actually get the final solutions, we would just continue on the path of using the full quadratic formula. Okay. Okay. So with that being said, let's go back to discussing what the graphs of our quadratics look like. So what we're going to try and do is, based on this new information of the discriminant and things like that, I'm going to want to try and pull information from our quadratic graphs, okay? So information from quadratic graphs. And this really shouldn't be a huge mystery for us, okay? I'm just putting this almost out as a formality, but let's look at 3 examples here and then what that tells us about maybe the A value, right? Or the discriminant, the D, and everything like that. So first one might look, let's say something like this. So I'll draw, and let's say our graph looks like, I don't know, something like this. Okay. What this tells me is that the A value, right? So according to my formula, ax squared plus bx plus c, right? The A value is going to be a negative number, and that's because we opened down, right? We talked about this last time when we discussed the graphs of quadratic functions. And now A is going to be negative, we open down. And we also know that the discriminant here, the D value, is going to be positive. And the reason I know that is because right now it's very clear that I have 2 real solutions on the graph, right? I visibly see 2 crossings, 2 x-intercepts. That means I have 2 solutions, and that only can happen when the discriminant is positive, okay? Similarly, we can draw another graph. Let's say I have something like this, and I've got my graph that kind of goes, I don't know, up like this, right? Okay, well, A is obviously positive, right? Because we open upward instead of downward. And our discriminant is actually going to be less than 0. It's going to be negative, and that's because we have 0 real solutions, right? You're not seeing any solutions on the graph, right? There are no x-intercepts at all. That means there's 0 real ones because we can see real solutions on the coordinate system. You cannot see imaginary solutions on a real coordinate plane, okay? So our normal xy that we talk about, that's only for real numbers. And so you won't see anything that's not real on something that is meant for real things, okay? Last but not least, another graph, really quick. Let's say we have something like this. And maybe my graph looks like this. It intersects right there at the origin. What we know is, well, A is still less than 0, right? It's negative because we're going down. And we would also know that the discriminant here, or D, is equal to 0. And that's because we have 1 real solution. Okay, the 1 solution is the 1 crossing that we have. Okay, awesome. So again, something we probably could have figured out on our own, right? This is not something new necessarily for us. It's just kind of a categorization of what the graph does versus really what the discriminant would mean in our A value, which we kind of already had an idea from the previous conversation on graphs. Okay. All right. So from here, we're going to shift gears, and I want to start to discuss those complex solutions. Right? So again, if our discriminant, we go back up, we said if our discriminant here was a negative number, right? We got a square root of some negative thing. That was going to lead to 2 complex solutions, okay? So we're going to start off by just figuring out what in the world that means. So here, I'm going to put complex / imaginary numbers. Okay. So what does this all mean? Okay. Well, first things first, let's talk about the standard form of a complex number, and that is a plus bi. Okay, a plus bi. So in this case, the a value is the real part. So this a value here is the real part of this complex number. The b value is the imaginary part. Okay? So when we talk about a complex number, it has a real part and it has an imaginary part to it. Okay? It also, as you can see, has this I value, which we haven't talked about yet, but the I value, I, is actually equal to the square root of -1. Okay, so I is equal to the square root of -1. This is going to come into play later on, and you can imagine even still with when we're doing the discriminant, right? If there's a negative number, there's going to be an I involved because the negative number can be handled by just putting I into the problem. It'll get rid of that negative sign for us, okay? So this is the standard form of a complex number, right? There's a real part which has no I on it, and there's the imaginary part which has the I multiplied, okay? Now, we're going to say to work with square roots involving negative numbers, we need to use this I value, right? We need to use I, which is equal to the root of -1. Now, not only is I going to be equal to the root of -1, that's going to tell us information about I squared and I cubed and I to the 4 and any power that we're going to put on I, okay? So here, let's write these out again. So starting off I, right, square root of -1. I squared, well, just as you'd imagine, it's square root of -1 squared. We talked about the square root and the square canceling out, and this would give us with -1, okay? So I squared is actually equal to -1. I cubed would be, well, we can either just kind of cube the original thing, or I can rewrite it a little bit tricky by doing I squared times I, right? So multiplying same base would add their exponents. 2 plus 1 should give us the 3. And what we know is that I squared is actually -1, and I is just I, right? So this would be -I, and then I to the 4 is just, again, same kind of logic, I squared squared. Power to a power, you'd multiply here, so that would be 4. I squared is -1 squared, gives me +1. So what do we notice? Well, there's kind of a pattern, right? We get I, -1, -I, 1. If you were to go to I to the 5, I would just take I to the 4 times I, which is 1 times I, or I. So this brings us back to this. I6 would then be equivalent to, as you can imagine, I squared. I7th would be then the same thing as I cubed. I to the power of 8 would then be I to the 4. And if you continued this up to some higher power, you are just going to try and basically figure out how this dumbs down to the first 4 starting ones, right? Because if you know the first 4, I squared, I cubed, I to the 4, then you can figure out something that's got a way higher power, right? Just basically what I would do is figure out how many times it goes into 4. That way you can dumb it down all the way to the starting thing. So as an example, let's say I want to do I to the, I don't know, let's say 71st, right? So the question becomes, how many times does 71 go into 4, right? And so if you did 71 divided by 4, I'll just put this as an aside here, 71 over 4, this becomes 17.75, right? Or as a mixed number, this would be 17 3/4, yeah? So what that means is I can essentially go back, right? I can use essentially 17 I to the power of 4s, right? So I to the 4, which is just 1, there could be 17 of those, right? And so, right, again, 17 times the 4 would be the 68. And then there would be 3 left, right? Based on this same logic I'm thinking of, right? So I was able to take out 17 of them, and there was 3 out of the 4 left over, so there would be an I cubed here. This part is just 1, right? I4 is just 1. 1 to the 17 would just be 1 times I cubed. So we can convert something that's got a really high exponent into something that's got a very small exponent that we know how to do. And then I cubed, remember, was just equal to negative I. Okay, so that'd be it. This would be kind of how we break something that's got a really big power down to something that has a smaller power, and then we want to get what that's going to be. All right. Okay, hopefully that's making some sense. Now, one other thing I want to note with these is that you can do, so let's write this out here, you can do arithmetic, and I just combine my H and my M here, arithmetic. We can simplify, and we can solve equations with complex numbers the same way you do with real numbers, right? So hopefully we're kind of already seeing this as we're solving some of these, but essentially we're just going to do everything the exact same that we have done, right? Whether the solutions are real or imaginary, we're going to solve everything the exact same way. And then we just might happen to end up with, a square root that's got some negative or something in it. That would just be an indicator for us that, oh, well, our solutions are just going to be complex instead of real. Okay? And that's okay too, right? So in this unit, this is where we're going to start to see we might have to classify these specifically as either real or imaginary. And then if they are imaginary, we're going to want to solve what those actually are. Okay, so it's not going to be good enough for us to say, oh, we have 0 real. It's like, okay, well, we have 0 real, but that's going to mean we have possibly those 2 imaginary. What are those 2 imaginary solutions, right? Okay, so let's just practice a couple similar to this one I was doing up above, just working with our I values and everything like that. I'll put a bunch of practice problems here. We'll just kind of work through. We'll start with the first one, which is very similar to the top one I did, something like I to the 32. Okay. So the goal is to simplify this, right? I to the power of 32, they're going to say simplify. What is this going to be equivalent to? Well, a couple of different ways, but like we saw previously, right? If I put it in terms of I4, I to the power of 4 is equal to 1. I know that 8 times 4 is 32. And so this is the same thing as just like 1 to the power of 8, which is 1. Right? I could also do this in terms of I squared. Although personally, I think that the larger the value, the better this becomes because you can take a lot more out and you'll solve things a little bit quicker. But if I did the squared, this would be power 16, right? 16 times 2 would be 32. And I squared is equal to negative 1. And negative 1 to an even power, if you multiply this out, would become a positive, right? So negative 1 squared is 1, negative 1 to the 4th is 1, negative 1 to the 6th, to the 8th, to the 10th, any even number will be a positive number. So we get positive 1. So no matter how you do it, you're going to get the same result, right? So this, or the list could keep going, right? We could do any kind of combination of that. Okay. Another question we might see is given something like 15 plus 4i, identify what the real part of this is and what the imaginary part is. All right, that's not a mystery either, right? The real part is, like we talked about, the part without the I. So 15 would be the real part. The imaginary part is the constant or the coefficient in front of the I. Don't put the I as part of the imaginary part. It's not part of that, right? The fact that this is the imaginary part is because it's being multiplied by I, right? The I is the kind of imaginary thing. This is just making it a part of that imaginary thing, right? So 4 is the imaginary part. Don't include the I, okay? That's totally separate. All right, another one. negative 3 minus 5i. The real part is going to be negative 3. The imaginary part, negative 5. Okay. Now note they might rearrange these. Usually, like I said earlier, we put the real part first. We put the constant here, but they could easily have said negative 5i, minus 3. And you would still need to identify this is the real part, this is the imaginary, right? So just because they put this first, that's not the reason why that's the real part, right? The first number you see is not the real part. It's the number that is by itself without the I, that's the real. Okay? So if they rearrange it, just note that you don't just take the first thing you see blindly and call that the real part. That's not how that works, right? It's the thing with the I is the imaginary part. The thing without the I is the real part. Okay? All right, cool. So hopefully that makes sense. Now what we're going to do is take a look at some stuff that's involving negatives under our square root. So for example, something like square root of negative 9. Okay. This is the same thing as square root of negative 1 times square root of 9. Remember, multiplication, we can split those up, right? We can split the roots up, having the individual terms that are being multiplied. So we can have negative 1 times 9. That would be the negative 9. The first part is I, and square root of 9 is 3. So this would come out to be 3i. Super simple, right? Another one would be square root of negative 16. Imagine the same thing. You take the negative 1 out, you're left with root 16, which is 4. You get 4i. Now, as we've seen previously, you might not have a square root of a number that you can solve for an integer, right? So it's not like a perfect square root, and that's totally cool as well. So something like root negative 10, you do the same procedure, and you don't really need to write this middle step out. It would be totally sufficient to just say this becomes root 10 times I, right? So you would break up the negative 1 and then the 10, and then the root 10 doesn't do anything, right? Because there's not a way to simplify root 10, and the I would just stay. Remember, we're putting this part times I. Usually you're not going to see I times root 10, although it is possible for you to write it like that. Generally, like we said with the complex number form, it's A plus BI. A comes first, the real part, then it becomes the imaginary part, then the I value itself. So there is like always kind of a set accepted order for these. I would just continue to follow that same order, right? What else? Let me do a few more of these just to really solidify us here. Something like negative 4 times square root of negative 4. This would be negative 4 square root of negative 1 square root of 4. And again, I probably would go right here straight to the answer, but I'm going to write out the steps so we can kind of start to see it. And then as you get better and better, maybe you skip some steps as well. But this would be negative 4 times I times square root of 4, which is 2. All in all, that's negative 8i. That would be your answer. Okay. Cool. Another one. 7 plus square root of negative 121. Well, negative 1 comes out, 121. We get 7 plus square root of 121 is going to be 11. And then, of course, square root of negative 1 is I. So 7 plus 11i would be our solution there. Okay. Hopefully these aren't feeling too crazy. This is really just implementing this I value. But based on what we had set up above, right, we can use these complex values, these I values, to actually solve things the same way we would have done with things that have real values, real solutions, stuff like that, right? So just imagine any scenario we previously solved for, we can just do the exact same thing, but now introducing these I values. So as an example, I might do something like 3 minus 19i times, or let's start with addition and subtraction, I guess. Let's do plus 7 plus 5i. Okay. Here, treat the I value almost like it's a variable, right? So if this was like an x or something like that, you would combine like terms that also had that x in it. This I, you're going to combine things that have another I as well, and those are like terms. If it doesn't have an I, you're not going to combine them, right? So here, I don't really need the parentheses anymore, right? I'm just adding. So this would be 3 plus 7. So you can combine those, right? You just kind of ignore these all together now. 3 plus 7 would be 10. Negative 19i plus 5i. Negative 19 plus 5 would be negative 14i. Right? So the constants without I go together. The things with I also get combined together. And notice how I put this in the form of a complex number, right? A plus bi, right? A plus bi. Here b just ends up being negative 14, but it's still in the form. Okay. You can also do subtraction, right? So addition, totally fine. Subtraction works the same way. So let's do something like negative 2 minus 7i minus 8 plus 3i. Again, negative 2 minus 8 is going to be negative 10. Negative 7 minus 3 is going to be negative 10 and then the I with it. So negative 10 minus 10i would be my solution there. Cool. Okay. Again, same as what we've seen, right? You're just adding or subtracting terms. If they're like terms, so if they have, for example, the I in it, you combine those. If they don't have the I in it, you combine those because those are also like terms. We could also do multiplication division, right? So something like 5i times 4i would be 20i squared, right? Again, treat it as if it was almost like a variable, right? What's I times I? It would be I squared. I squared is negative 1, right? You're going to have to remember those things from up top, right? If I is root negative 1, I squared is negative 1. This is negative 20 then, okay? All right, easy enough. So that's how that's going to work, okay? And hopefully we feel pretty comfortable with that. Just remember what I squared, I cubed, and I fourth is, and then plug those in as needed. Let me do one more just to kind of solidify this because we might also see something like this. This might be two terms multiplied similar in this form, but I'm going to do it as like a squared one just to really emphasize what this is. So let's say I have 1 plus 3i, and I'm squaring that. Please, please, please remember that this is 1 plus 3i times 1 plus 3i. Do not put this as 1 squared plus 3i squared. That is not what this is, right? You cannot do that because of this addition, right? Addition and subtraction, you can't just take this exponent and apply it to each one and call it a day. That's not how this works, right? You're going to miss a middle term because you have to distribute everything, okay? So let's look at this. When I write it like this, I get first, outer, inner, should be I, 3i, and then last, 9i squared. So note, 3i and 3i is 6i. 9 times I squared is 9 times negative 1. I squared is negative 1. This is minus 9. What you get is minus 8 plus 6i. That would be your answer for this, okay? Like I said, do not put 1 plus 9i squared. Don't put that, right? It's not this squared and this squared by itself. You have to go ahead and write this out and actually do the distribution. So it's not going to equal, this would be minus 9. It's not going to equal negative 8. Clearly, right? That's not the answer. Okay, good. So again, keep all this in mind. Do the process the same as we would normally do it. If you're adding them, combine like terms. If you're multiplying, multiply everything out. Just make sure you're using the correct things for I and doing the actual distribution properly. Okay. Now, on top of these complex numbers, there is something else that we want to keep in mind, and we want to know that complex numbers have complex conjugates. Okay? So complex numbers have complex conjugates. So what does this mean? Well, if a plus bi is your complex number, then a minus bi, which is literally just the same thing, the sign in the middle gets changed, right? The sign on the imaginary part gets changed. This is its conjugate. Okay? So complex numbers, they have these conjugates. It's the same format. You just change the sign on the imaginary part. Okay? So instead of plus b, it became minus b or vice versa. Okay? Now, something else to think about is when you multiply a complex number by its conjugate, the result, right, what comes out of it, the result is a real number. Okay, so when you multiply a complex number by its conjugate, you are going to end up with a real number. Okay, awesome. Something else to say, right? Something else. One last thing. So we know what the conjugate is supposed to be. We know what happens when you multiply the number, right, the complex number by its conjugate. I also want to mention that complex numbers, they come in pairs, right? So these complex numbers come in pairs. So what that means is you have the complex number and its conjugate are going to be together, right? So when you talk about like solutions, think back to the quadratic formula. If your discriminant was negative and I said, hey, you have two complex solutions, you're going to have a value and its conjugate, right? Because the conjugates come in pairs. So once you get one complex solution, you're guaranteed to have its conjugate as the other complex solution, right? Because these complex numbers have to come in pairs when we see them, all right? So let's kind of talk about this in the scope of some problems, right, to try and make sense of all of this. So first things first is what happens when I take 2 plus 3i and multiply by 3 plus 4i? Well, what we should see here is that these are not conjugates of one another, right? 2 plus 3i, its conjugate would be 2 minus 3i. This is clearly not that, and vice versa. This is not 3 minus 4i. So I'm not expecting to get a real number out of this because they're not conjugates. I'm just expecting to get another complex number. So let's do this. 2 and 3 is 6, right? Just distribute this out. 2 and 4 would be 8i. 3 and 3, 9i. 3 and 4, 12i squared. Like we talked about, these come together to be a 17i. This becomes a negative 12. I squared is negative 1. 6 minus 12 is negative 6 plus 17i. Okay, well, look at that. Something that is not a real number. It's complex because it has the I in it, right? No mystery. I was expecting that to be the case. And let me clean this up here. Just this looks like 17. Okay. Fine. Let's try another one. What happens when I take 2 plus 3i and I actually multiply it by its conjugate? 2 minus 3i. Right? Now I'm expecting to get a real number out of it. Let's distribute. 2 and 2 would be 4. 2 times negative 3i is negative 6i. 2 times positive 3i is positive 6i. 3 and negative 3 would be negative 9i squared. These are going to go away, right? Plus 6i minus 6i, you're going to get 4 minus 9 times negative 1, right? So that's positive 9. You get 13. A real number, right? As expected. When you multiply complex number by its conjugate, you get a real number. Okay. Easy enough, right? And again, this could extend however much. No, one more example here. Negative 7 minus 10i, negative 7 plus 10i. Note again, these are conjugates. The only thing that's making these a conjugate is by changing the sign on the imaginary part, right? It doesn't matter about changing the sign on the real part, okay? That's not going to make it a conjugate. You need to change the sign on the imaginary part, the part that has the I with it, right? So these are conjugates. I'm expecting to get a real number out of it. I just have to do the multiplication. So negative 7 is positive 49. This would be minus 70i plus 70i. Those are going to cancel. and I get minus 100 I squared. With that, 49 plus 100, right? This becomes negative. Two negatives cancel, make it positive. We get 149. Okay, awesome, right? We're working with complex numbers, okay? We got these conjugates. We're starting to see how all of this is working, all right? So the last thing I want to do, which is going to kind of start to talk about this pairing here, I want to start talking about how to use or how to necessarily solve quadratics with complex solutions. Okay, so that's what I'm going to do next. And this is going to be the last thing we cover for our quadratics for Unit 10, and then we are done with the material, okay? So let's talk about quadratics with, I'm not spelling anything right today, quadratics with complex solutions. All right, so let's give an example, okay? X squared plus 2x equals negative 10. What do we get? Well, x squared plus 2x plus 10 equals 0. Remember, we want it to be equal to 0 when we set this up using the quadratic formula or really any other technique you're going to do. Here, I don't know if this is going to factor perfectly. I have a feeling not. If you really wanted to know if you had real solutions or not, we could just start with the discriminant, right? So let's just do that. Let's see what the discriminant gives me. That way I'll even know if I should start factoring this to find real ones or if I am just going to have, complex solutions. So here, b is 2. 2 squared minus 4 times 1 times 10, a and c. This becomes 4 minus 40. Clearly, this is less than 0. I'm going to have two complex solutions. Cool. I'm going to have two complex solutions. Let's solve what those complex solutions are. So using this kind of already, right, I'll set it up negative b plus or minus r squared of b squared minus 4ac, which is square root of negative 36, all over 2 times a, 2 times 1. Okay. Negative 2 plus or minus square root of 36 is 6. The negative under the root can be used up by putting an I in over 2. This is going to be negative 1 plus or minus 3i. So those are my two complex solutions. And note, when you draw this on the xy plane, right, you draw this quadratic, you're not going to see it ever cross the x-axis, right? So if you draw this, it's going to open up and it's going to look something like this. Okay, it's never going to cross the x-axis because we on the xy plane only see real solutions, right? We only see real values. In this situation, these are not real, right? These are imaginary. You're not going to be able to see those on our real coordinate system. Okay, good. Hopefully everyone's feeling okay here. I know there's some algebra to do on this, but this might be some of the easier algebra we have done. It's literally just plugging into a formula that hopefully we have memorized. Let's try another thing. Y squared plus 10y plus 44 equals negative 1. Again, I'm going to try and solve this. Note that this is a quadratic. I just changed my variables from x to by. It's not a big deal, right? I can make the variable whatever I want. So first step, as usual, is I'm going to put everything on one side, make this equal to 0. So 45 equals 0. Okay. Again, I don't really know. This could factor, but for the sake of it, I'm just going to automatically jump to the quadratic formula. Here, if I use the quadratic formula, I'm not even going to check the discriminant beforehand. I'm just going to do this, okay? And then while I'm doing it, I'm going to see what the discriminant gives me, and then I'll have a guess as to what my solutions are going to be. But I'm just going to go straight through and plug in, okay? So let's do this. Negative b plus or minus square root of b squared minus 4ac all over 2 times a. So what do we get? We get negative 10 plus or minus 10 squared is 100. 4 times 45. 45 times 2 would be 90 times another 2 is 180. Keep going. Negative 10 plus or minus, that's square root of negative 80. So 80, right? Again, factor tree if we need to do it. So 80 could be, in this case, what do we think? Well, could be 16 and 5 if we get really good with it, right? To notice that square root of 16 has a value right off the bat, right? So root 80 could be root 16, root 5, which root 16 is 4. So this could be 4 root 5. And then the negative will get handled by putting an I value on it over 2. Make this look like a 10. And therefore, what do we get? Well, split this up, right? Top is being added or subtracted. That's totally fine. I can then just split these into two fractions. Negative 10 over 2 is negative 5. 4 over 2 is 2 root 5 times I. These would be my two imaginary solutions. And I would have expected there to be imaginary solutions because when I went through with the discriminant, I got negative 80, right? So the negative 80 told me that it's less than 0. I'm imagining there's two complex solutions because of the fact that I'm taking the square root of a negative number, which I can't do in the real coordinate system, right? I can't do that in the real plane. Okay, good. Hopefully this is all making sense. Plug into the quadratic formula, see what you get your complex solutions at the end of it. Now, what I will say is there are some special cases where even if you do have a quadratic with complex solutions, you don't necessarily have to use the quadratic formula. And this is really just going to be in the case where you have something like this example where you really don't have like that middle term at all, right? So you can kind of solve this using the square root technique that we talked about previously. So something like this, I could take, oh, well, x squared would equal negative 21. X would then be plus or minus the square root of negative 21, which means that x is either plus or minus root 21i, right? So positive 21, positive root 21i or negative root 21i. Super simple, right? We don't have to kind of use the quadratic formula, although you could, right? You could technically use the quadratic formula for this as well. Just note that b is 0 here, right? There's no middle term with x. So if I just solve that, just to really emphasize this, a would be 1, b would be 0, c would be 21 in this example. So our solutions would be negative b, negative 0, plus or minus b squared, 0 squared, minus 4a c, all over 2a. So what do you get? You get literally plus or minus root, this is 4 times 21, so negative 84 over 2. And then what would this be? Well, 84, think about your factor tree, would have to be 21 and 4, right? Pretty easy. 20 times 4 would be 80. 1 and 4 would be another 4, 84. Okay. Now you don't know root 21, of course, but you do know root 4 is 2. So this becomes plus or minus 2 root 21i. Get rid of the negative on the inside with the I over 2. 2 and 2 go away. Plus or minus root 21i. Look at that, same solution. Okay. So we can use the quadratic formula always, right? It's totally okay. You just might be able to solve something a lot quicker without it. Okay. So don't think you're really stuck having to do the quadratic formula. Most times, if the problem's a little bit more complex like these ones, maybe it's just worthwhile jumping there right away. But for something like this, where it's a much simpler kind of setup, I would just recommend solving this by hand, as you would normally do with the root process. Okay. Another scenario, super similar to this, would be y squared plus 7 equals 0. Same setup, right? Y squared is negative 7. Y would be plus or minus the root of negative 7, which means y is plus or minus root 7